Good afternoon, and thank you for joining us for Ryerson's Metal 102. My name is Stephen Taggart, and it is my pleasure to be your host on this immersive and interactive journey into the world of fabrication. For the next hour, we will dive headfirst into all aspects of fabrication, from sheet to plate to long products. Our subject matter experts will lay out the key factors that go into identifying the most efficient supply chains. As you can see from the map on your screen, we have created a university experience. Our curriculum is based on the collective knowledge and expertise of Ryerson over the past 180 years. I will be your guide and make sure you get to each class on time. Let's take a look at our class schedule for today. We will spend roughly 10 minutes at each classroom: intro to fabrication and elements of a print, long products, plate products, sheet metal products, and quality. Matt, Printmaster Stelzer, will lead intro to fabrication and the elements of a print. Zach, the long game Hicks, will educate us on long products fabrication decision-making. Ray, Plate Expectations Fleming, will teach plate products fabrication options. Jarrett, Sheet Music Jones, will talk all things sheet metal fabrication. And Ian, ISO Toth, will give an overview of Ryerson's quality commitments. You'll have an opportunity to ask questions at the conclusion of each class. Do so by using the Q&A button at the bottom of your screen. We'll try our best to answer them live, and if our team does not get to them, we'll follow up after today's presentation. And yes, the full Metal 102 video will be available starting tomorrow on Ryerson's YouTube channel. So, without further ado, class is starting. We don't want to be late. Professor Stelzer is ready to lead Intro to Fabrication and the Elements of a Print. He is very strict when it comes to being on time, just like Ryerson and their on-time delivery. They are all yours, Professor Stelzer. Take it away.
Thank you for the introduction, Stephen. Welcome to Metal 102. My name is Matt Stelzer. I am the Inside Sales Manager for Ryerson Advanced Processing Division that covers Ohio, Michigan, Indiana, Kentucky, and Western Pennsylvania. In my class, we will cover some industry terms and definitions that will repeat throughout the course. I will list some of the more common types of processing when it comes to sheet, plate, and long product fabrication. You will learn about CAD file types and how each file type is specific to the part and how it's interpreted in the manufacturing process. I'll wrap up my time with you today by reading through a title block and identifying its features. We have a lot to uncover, so let's get started. Let's begin the class with a few definitions and terms. The first term is fabrication. Simply put, metal fabrication is defined as creating products or structures by cutting, bending, and/or assembling metal material. It's largely considered a value-added process as it consists of putting together actual products or structures from raw material. What is a blueprint? Blueprints have many names and are also known as drawings, manufacturing prints, engineering drawings, or simply just prints. Most prints are white and have black lines, but they're still often referred to as blueprints. Think of a blueprint as manufacturing instructions. They originate in the engineering department, and they give the manufacturing department all the information that is needed to make a product. Blueprints transform ideas into products and communicate information between engineering and manufacturing. The three basic elements of a manufacturing print are the drawing, the dimensions, and the notes. Prints contain all the information that is needed to make a finished product. A finished product may be anything from a simple part to a complex assembly. Quantities of parts to be made range from one to millions. Manufacturing organizations use blueprints range in size from small machine shops to large industrial corporations. In all cases, prints provide the information to manufacture a product. Most manufacturing prints have a title block, and within the title block are the manufacturing tolerances for that part. The tolerances are critical for how the parts fit together with other parts. Tolerances are communicated in fractions and decimals and can be in metric or in inches. The part tolerance can also help determine what process is chosen to manufacture that part. Part tolerances can be matched to machine process tolerances that are best suited for producing the part on the drawing. Another industry term is kerf, or the material that is lost as part of processing. Different cutting machines like laser cutting, plasma cutting, or oxy-fuel cutting remove different amounts of material due to the type of gas or electricity used to make the cut. Machinability is how hard or how easy it is to remove material through the machining process, or whether it's a carbon or alloy or stainless or aluminum, each type machines differently. There are many factors that go into a part's machinability. Our sales engineers at Ryerson are well equipped to handle a variety of material types and processes. The last term on this slide is nesting. We want to be able to fit as many parts onto a stock plate or sheet as possible to improve yield and maximize material usage. Part nesting can be achieved using computer-aided design software that allow the user to import files and manipulate them on a 2D plane. Now that we have some terms and definitions identified, the next step is to identify what process should be used to manufacture the part and how many processes are needed to get a finished part while still meeting the criteria outlined on the print. The more complex the part, the more processes will be required. There are many different processing methods. Let's look at a few first stage processes. Some common types of processing you may be familiar with are laser, plasma, or oxy cutting. All three of these are considered thermal cutting because they use heat to cut through material. Laser cutting, and this term could be flat laser or tube laser cutting systems. Lasers use either oxygen or nitrogen to cut through the material and are ideal for a wide variety of ferrous and non-ferrous material. Today's flat laser cutting machines can cut up to 2-inch thick carbon. Plasma cutting uses electrically charged gas to cut through the material. Plasma cutting is generally used for parts up to 2 inches thick and used to cut stainless and carbon and alloy steels. Oxy-fuel cutting is another thermal cutting process similar to plasma, but without the ionized gas. Oxy-fuel cutting uses 99.5% pure oxygen to create a flame capable of melting through the steel. Oxy-fuel machines can cut up to 22-inch thick plates. Water jets do not use heat to cut through metal. A benefit to not using heat is that there is no heat-affected zone around the cut surfaces. Water jets use a high-pressure stream of water with sand or other abrasive material to cut through a variety of metals and plastics. Second stage processing follows after the first stage. Think of this as now you've got a first stage cut blank, a plasma cut blank or profile, and now you've got to put additional holes into it or create a new shape out of it. One way to do that is through forming or metal bending, which is a process in which force is applied to a sheet or plate to create a bend of a specific angle. This is typically achieved using a press brake with a punch and a die set. Ryerson's family of companies has the ability to form parts that are 40 foot and longer. Machining is a manufacturing process that uses various types of cutting tools to remove small amounts of material from the workpiece to ultimately produce a high precision part or component. Milling machines tend to be used for drilling or cutting shapes into a hard solid material. Rotary tools on the milling machine can shave and slice a material in varying directions, depths, and angles, and range from 3 to 6 axis structure. Lathes are not too dissimilar to milling machines in that they both shape the desired material using spinning contact between the machine's component and the object. However, while a milling machine tool spins and or moves to the work on the still material, the lathe rapidly rotates the material while introducing the tool to shave and shape the spinning object. Because of this method, lathes are best used for conical, cylindrical, or spherical shapes. Rolling, traditional rolling is cylinder rolling is a process of passing steel, sheet, or plate between a set of mechanical rolls. The goal there is to create an ideal curvature to form cylinders, tubes, or other shapes. And finally, heat treating. Heat treatment is the process of heating metal without letting it reach its molten or melting stage, then cooling the metal in a controlled way to select desired mechanical properties. Now that we know what a print is, we have some terms and definitions that will help us through the rest of the course, and we've covered some common processing methods that include both first and second stage processes. We can discuss 2D and 3D design and the term CAD. A CAD file is a digital file format used by computer-aided design software to create 2-dimensional or 3-dimensional designs, drawings, and models. It contains information such as geometry, dimensions, materials, and other specifications necessary for creating a physical product or structure. CAD files can be saved in various formats and can easily be modified, shared, or printed. They are widely used in industries such as engineering, architecture, manufacturing, and construction. The main difference between 2D and 3D CAD is the level of detail and realism in the design. 2D CAD is used for creating two-dimensional drawings that represent the physical dimensions of a product or structure in a flat, top-down view. In the manufacturing industry, think of a burnout or parts that are cut in the flat. 2D CAD designs are simpler, easier to create, and require less computing power than 3D CAD designs. Examples would be a DXF or a DWG file. 3D CAD, on the other hand, create three-dimensional models that represent the physical shape and appearance of a product or structure in a more realistic way. It allows for more detailed and accurate designs, including the ability to view and design from multiple angles and even simulate how it will behave in the real world. 3D CAD designs are more complex, require more computing power, and are often used in industries such as product design, architecture, and manufacturing. 3D CAD is great for parts that are not flat or have features that cannot easily be seen in a typical view. File types include IGS, SolidWorks, and step files. So you may be asking, how are CAD files different than shop drawings or the manufacturing print? Well, the drawing is used to validate the data in the CAD files. While the information contained on both are similar, the shop drawing typically includes more detail than just an electronic CAD file. Drawings have detailed dimensions, locations, and often include a bill of materials with quantities. They also include a title block, general notes, plan views, elevations, sections, and details. Whenever possible, send both the drawing and the CAD files. Next, let's take a closer look at the title block. The title block is usually found in the lower right quadrant of the drawing. It contains critical information and acts like a roadmap to making the part. On the screen, you'll see a typical title block found on most manufacturing prints or shop drawings. Some of the critical information in the title block include the unit of measure. In this case, the part is dimensioned in millimeters. The tolerance block. This gives us the allowable deviation from the specified dimension of the part. If the dimension on the cut piece is too far above or too far under the allowable deviation, then the part's no good and cannot be shipped to the customer. Part tolerances can be a guide in selecting the most suitable processing method. Material and finish. In this example, the part is plain carbon steel with no finish requirement. Then you have the description and the drawing name, number, and revision. It's very important to include revisions as parts go through engineering changes. The part number is used to identify the part and is typically referenced on all manufacturing and shipping documentation all the way through to the invoice. That sums up the element of a print. What I hope you take away from this is that there are many different fabrication processes. You don't need to know all of them. Let Ryerson's advanced processing team select the right part for you, the right process for you. Also remember that the drawing file provides us with the instructions on how to manufacture the part. The CAD files provide accuracy and speed and contain a lot of information but lack some critical details only found on the manufacturing drawing or print. The print validates the CAD files. They work together. The title block contains a ton of information, but is also part of the instructions necessary to make sure the part is made correctly. That concludes the introduction to fabrication. Thank you for your time this afternoon. Back to you, Stephen.
Thank you. Great job, Professor Stelzer. That's a great overview of how fabrication data is shared. The floor is open to the class for any questions. Use the chat button at the bottom of your screen and ask away. All right, we have a question from the audience. Matt, what does the term manufacturability mean? You're on mute, Matt.
You say manufacturability?
Yes.
Without going to a dictionary, I guess that just means how easy or how difficult it is to manufacture a part. You'll learn in this course there are a lot of different ways to get a finished part, but some ways are more efficient, more affordable, and just easier to do. Send us the print, send us the requirements, and we'll determine the right fit.
Okay, I've got one more before we move on. What are the main differences between nitrogen and oxygen cutting?
They're two different gases. I'll probably let Jarrett take that one, as he is probably better suited to answer that question. He'll actually touch on that here in a little bit. But oxygen does create an oxide edge. So if the part needs to go through some sort of powder coat process, nitrogen will be a better fit if the part allows for cutting with nitrogen.
Okay, thank you very much. We are now going to follow 3 parts representing 3 different categories from print to a finished product. Let's head over to the Long Products campus to kick it off. Talking about long, did you know Ryerson has been in business since 1842? Now that is a long time. Good afternoon, Professor Hicks. Take it away.
Thank you, Stephen. Good afternoon, everyone. My name is Zach Hicks. I'm a fabrication outside sales representative based in Minneapolis, Minnesota. Today, we're going to be discussing long products processing. Here's a print of the part we'll be using for this exercise. This is a 2-inch square carbon tube with a 3/16 wall. This particular part is generally ordered in either 120 or 240 piece quantities. There are many options for processing tube. Today, we're going to talk about the 3 most popular in the industry. The first option would be machining. For those of you not familiar with machining, these machines can make precise cuts with high accuracy and repeatability. The features and tolerances on this part does lend itself well to being processed on a lathe with live tooling. One potential bottleneck with that would be that the operator needs to manually load and unload each part. Second option would be a tube laser. Tube lasers can cut tubing, channel, structural shapes to length while adding holes or complex cutouts at the same time. Tube lasers can also make precise cuts with high accuracy and repeatability, as well as utilizing an auto feed option for raw material stock. That eliminates any inefficiencies that may come from the operator having to manually load and unload each part. Also makes this process ideal for high volume runs. Third option would be to hand process. That would be to utilize traditional machines such as a Bridgeport, drill press, or bandsaw to achieve the finished part. For a one-off or a prototype part, that may work, but it would not be efficient for a run with any sort of volume to it. This process would require fixturing as well as multiple tool changes and would be a very labor and time-intensive process. Our ultimate selection then would be the tube laser for 4 primary reasons: efficiency, repeatability, speed, and cost. Let's take a look at these machines in action. Couple key takeaways here. Major benefit of tube laser processing is the reduction of secondary operations. Cutting a tube with a physical blade often leaves metal shavings and some imperfections in that cut edge. These issues would require additional cleaning, deburring, or shapings to prepare the tube for whatever purpose it would be intended for. Another benefit is that there is no mechanical force that's applied to the cut. Normally, using a CNC punch or another machine would break through the wall of the material with physical force, applying stress to the surrounding material and slightly weakening it. Using a tube laser to cut helps to ensure that tubes are stronger at the point of the cut than they would be if a physical cutting tool was used. Lastly, and the most important part, is the diversity of cutting processes. CNC machinery enables a high degree of control and precision for many tasks. Our tube lasers are no different. Instead of simply making a vertical cut as you would on a saw, for example, you can make vertical cuts, angle cuts, slots, etchings, bevels, and much, much more. Thank you for your time today. Let's send it back to our host.
Thank you, Professor Hicks. I will never look at the tube the same way again. Ryerson has tube lasers strategically positioned throughout the United States. Question and answer time. Find the chat button and fire away. I'll let you know that we are answering the questions with our team live in real time via the chat button. So if we don't get to you live, then we will be able to get to you either during this session or follow up afterwards. I've got one question for you, Zach. With tube laser, does it matter if the tube is ERW?
No, it does not. ERW, welded tube or seamless, we can cut. The only caveat may be if there is a particular call out on the print where the weld seam location would need to be.
Okay, one more. Can you tell us some limitations that tube lasers have?
Limitations depending, there are a couple. One would be, of course, the size of the tube in terms of a diameter or a wall thickness. When you get into longer tubes, 24 feet or longer, up to 40 feet, you can run into some mechanical limitations of what they can handle pounds per feet. Our tube lasers can handle anything from the smallest, 3/16 round tube up to some of the larger ones at our facility in Norcross. It really is on a case-by-case basis. If we can't do it, say, for example, in Minneapolis, odds are we have another Ryerson location that could accommodate that.
I think the follow-up to that is send the prints to our team so we can evaluate and we'll find a solution for you.
Absolutely.
All right. Time to take our journey into the world of plate products. Did you know Ryerson can process plate up to 20 inches thick? Professor Fleming, you're at the plate. You see what I did there? I'm a jokester.
That's awesome. I love it. Thank you, Steve. My name is Ray Fleming. I serve as the Senior Account Manager within our Business Development Office. And thanks for joining us today for a journey through a few different options we offer in thermal cutting of plate products. The first process we're going to investigate today is laser cutting. Did you know that laser is an acronym? It stands for Light Amplification by Stimulated Emission of Radiation. It's a lot to say, but to put it simply, lasers work with a highly concentrated beam of light. We specialize in cutting all grades of carbon, stainless, and aluminum steel. The thickness range for laser cutting can easily run through common gauge thicknesses in sheet product and up to 1.25 inches thick in carbon steel. Advantages with laser cutting begin with the high precision cut quality. We can easily hold profile tolerances of 1 millimeter and hole tolerances as tight as 0.005 of an inch. Lasers offer a very smooth, clean, perpendicular cut edge, eliminating the need for post-cleaning operations. Lasers are perfect for 2D profile cutting of complex shapes and can accommodate almost any hole size, including irregular shaped cutouts like hex-shaped holes, slots, and small diameter holes that run smaller than the thickness of material. The next process we're going to look at today is plasma cutting. Plasma cutting is a highly charged electric arc over 20,000 degrees Celsius. A little slower than laser cutting, yet the range of speed available in traditional plasma can run up to 50 inches per minute. Plasma cutting begins at 3/16 of an inch thickness and can go up to 2 inch or 50 millimeter in carbon steel and up to 4.5 inch thick in stainless steel. Our high definition plasmas can easily hold profile tolerances of 3 millimeter or plus or minus a 16th. The speed and accuracy of plasma cutting makes it the lowest cost option. Profiles with radius corners are a perfect match for this process. With this increased speed, some profiles with tight 90-degree corners or small diameter holes might be better suited for laser cutting. Another huge advantage is our ability to add beveling capability right on the plasma table. We can bevel up to 45 degrees, eliminating the need for any secondary handling. And we can also include milling, drilling, and tapping operations to save that post-operational step of machining. Lastly, we'll look at the oldest type of processing, which is oxy-fuel cutting. This type of processing has been around for multiple decades. Just like it sounds, this method uses pure oxygen and an assist gas up to 1,800 degrees Fahrenheit. Another great feature of oxy cutting is having multiple torch capability, ranging in one single torch up to 12 cutting torches running at the same time. And as Matt mentioned earlier, oxy allows us to cut over 20 inches thick in carbon steel grades. Certain grades and heavier thicknesses require preheat passes to bring the base temperature of the plate up prior to piercing and cutting profiles. This type of cutting takes true craftsmanship, and our machine operators are the best in the business. Slower than plasma cutting, but able to hold tight corners in profiles with less bevel effect on the cut edge since they run at a slower speed rate. I've seen cut edges on our factory floor that would astonish you. The level of our cut quality is truly a testament to our seasoned professionals. Straightness and perpendicularity of our cut edges are unmatched in the industry. Now let's take a look at these cutting methods in action. I love to see those sparks fly. Some key takeaways: laser cutting, highly tolerance profiles, including holes and intricate cutouts. Ideal for slot and tab configuration that can reduce setup times for welding and eliminate the need for expensive weld fixtures. Plasma cutting, very fast, efficient method of cutting and very competitive cost due to its speed and accuracy. Oxy cutting, as I mentioned earlier, takes true craftsmanship. Just like a finished carpenter, our operators have the tenure and experience that is easily seen in the finished part quality. Back to you, Stephen.
Great stuff, Ray. Great stuff. Processing plate is a key core competency at Ryerson. Ryerson has over 100 plasma and oxy-fuel plate processing machines in the U.S. Q&A time. Let's see those questions. Ray, I've got one for you from the audience. What does it mean to hold tolerance?
To hold tolerance is just simply to hold the drawing tolerance. Say, for example, you've got a hole tolerance of plus or minus 20,000. So when I say we can hold tolerance, that means we will process that on a machine that can hold that tolerance, most likely a laser, and then measure it for accuracy to make sure that we are holding that tolerance. Great question.
What is the main disadvantage of plasma cutting over laser cutting?
Plasma cutting, because it moves so fast, it often cannot give you a sharp 90-degree corner. And when you're cutting small holes, sometimes they're not perfectly round. Whereas a laser, you can have that sharp corner and intricate cutouts, and then your holes can be cut at a much higher diameter tolerance.
Okay, one more for you, Ray, then I'll let you off the hot seat. No pun intended. Can any of these methods be used for aluminum, or are the temps too hot?
Actually, all laser cutting and plasma cutting can be used for aluminum. Oxy, no. So ideally, laser cutting is probably one of the best. Plasma cut can be done for aluminum as well. It all depends on material thickness, the complexity of the part, the shape of it, how many holes there are in it, what the shape of the holes are. So, and as we mentioned earlier, just send those prints into your Ryerson Advanced Processing team, and we'll sort that out and give you the best supply chain.
And you can upload those prints to wrap@ryerson.com. Again, that's wrap@ryerson.com. And we can take a look at those and help you find a solution. Next up is sheet metal fabrications. Did you know Ryerson is the largest aluminum and stainless steel sheet distributor in North America? Professor Jones, the chalkboard is all yours.
All right. Thanks for the intro, Steve. Hey, everybody. My name is Jarrett Jones. I am the sales manager at LaserFlex. We're a precision metal fabricator and a member of the Ryerson family of companies. We're located in the Greenville-Spartanburg area of South Carolina. So today, I'm going to walk through an example of a part being produced from carbon sheet material This specific example is being produced from 1/4 inch hot roll P&O or strip mill plate. So right out of the gate, let's go ahead and qualify what the annual volume is going to be here, because that's generally a pretty large determining factor in what end process we're going to use. So let's say that the annual quantity on this specific example is going to be 1,000 parts per year. All right. So what we want to do, our end goal is to determine what is the most viable processing method that meets all the tolerances and requirements of the customer, that also offers them the component at the best possible price point. Just a quick note here, this specific example, it does require a forming process. I'm mainly going to focus on the first stage cutting processes here, but if you have any questions about forming, don't hesitate to ask those. So I'm really going to focus on 3 main baseline cutting processes. Those are plasma cut, laser cut, and hard tooling or stamping. There are more out there, but these are generally the most common ones that you'll run into. Obviously, this isn't a test. Nobody's getting a grade here, so I'll go ahead and give you the answer. We're going to end up laser cutting this part. So what we're going to do, though, is kind of run through this drawing and figure out how we get to that answer using a process of elimination. So the first thing we want to do when we get an inquiry from a customer is go through the drawing, and we're really trying to determine, first, can we make the part? And then second, what is the most viable method? The biggest part of that is reviewing the title block and understanding the tolerances. So pretty quickly, looking at this drawing, I can tell that there's a hole in this part that needs a plus or minus 10 thousandths tolerance. So right out of the gate, that eliminates plasma cutting. Even today's high def plasmas, really the best tolerance you're going to achieve is plus or minus 30 thousandths. All right. So we can set plasma cutting aside for now. The next one we want to look at is hard tooling or stamping. So really a good qualifier for hard tooling is annual volume or the total volume of the part. So we established that a little earlier. Our volume is going to be about 1,000 parts per year, which is honestly pretty low for a hard tooling solution. So, for stamping, you're producing a specific tool to make a specific part. And the cost of those tools can be, $10,000 or more. So it can be prohibitive to lower volume items. There's also a pretty long lead time on producing custom tooling. So dependent upon, customers' need to get a product to market quickly, that can eliminate hard tooling, at least in the short term. And the other thing about hard tooling, for all of its cost advantages over the long run, it doesn't allow for a lot of design flexibility. So again, to do a hard tool solution, you're making a very specific tool to create very specific features in that part. Should you need to change the part, then you either have to reinvest that capital into revising the tool or getting a brand new tool. So through that process of elimination, that leaves us with laser cutting. So laser cutting can really exceed all of the tolerances that are on this drawing. It's super fast to market. There's not really any upfront, tooling or anything like that that's needed. There's no large upfront costs beyond just simply setting up the machine. And laser cutting allows for limitless design flexibility. So we can change the part right up until the point that we're actually cutting it, with no added cost or really downtime. With that, let's take a quick look at a video highlighting some of our state-of-the-art technology and processes. All right, pretty cool stuff. We continue to invest in the newest technologies that are out there. So, a couple of quick key takeaways here. Step one is just always to review all aspects of a drawing. Let's figure out what the tolerances are, figure out what the best processing method is for that specific part, and tailor our processes to that. Laser cutting can achieve super tight tolerances and is very cost effective. And laser cutting provides design flexibility. Again, we can basically change the part on the fly. That's all I have. And with that, I'll take any questions.
All right, great class. Ryerson has over 30 laser cutting machines strategically located throughout North America. Continue to ask questions to the Q&A button. Hey, Jared, what is more expensive, plasma or laser?
It really depends on the application. Generally, if you're going off of an hourly rate, right, an hourly laser rate is higher. That being said, the cost to operate a plasma is lower. So we really want to tailor that to the tolerances that are needed, the part size, the thickness of the part. It's really going to be part specific as opposed to kind of painting with broad strokes.
Do you need a DXF file with all laser cuts or with all laser cut opportunities?
So we love to have a DXF if we can get it. That being said, we can operate off of just a shop drawing or PDF. We can kind of reverse engineer that because we do have to create a DXF for the machine to understand what it's doing. So we have flexibility there. We can convert most files to something that's usable.
Last one for you, Jared. Can you tap a lasered hole?
You can tap a lasered hole. We do it a lot, but there are some things to consider. It does harden, the inside of that hole just a little bit. So you do have a higher propensity to snap a tap off in it, but we do it every day.
Okay. Thanks, Jared. While we're still on the subject of lasers, I'm excited to introduce our new fully automated laser cutting and press brake facility located at our Temper Mill facility in Portage, Indiana. This exciting state-of-the-art processing line is equipped to handle metal parts up to ½ inch in thickness and up to 60 inches by 120 inches long. Check out this video.
We recognized that there was an opportunity in the marketplace to put a world-class laser center right next to a world-class temper line. The old way of manufacturing a part, automation loads material onto a laser bed. From there, that's where it stops. What Ryerson has done is we've combined all those processes without any human intervention at all. So we have automation that loads the raw materials onto the machine. We have automation that cuts and moves parts. Robots that grab parts and form them, and additionally package them. The first time any human intervention is introduced is when they put a tag and a band on the product. The new laser center is all the automation that we could possibly fit inside of one machine to get everything done in one spot. That way we give you better lead times, better pricing, better reliability on delivery. We have competitors that have automation in laser cutting and maybe even some automation in forming. This is the first and only at the service center level in the United States.
Wow, that's really exciting equipment. And I tell you, very efficient. It can produce parts quickly, great lead time at a very competitive cost. So we look forward to quoting your projects using this exciting new line. Well, now that we're all laser focused, let's jump on the Ryerson bus to our next class. By the way, the Ryerson bus includes plate, sheet, and long products, but is powered by quality. Professor Toth, the wheel is yours. Take us away.
All right. Thank you for the introduction, Steve. Hi, my name is Ian Toth, and I'm a supplier quality engineer at Ryerson. I help manage our network of fabrication shops around the country, as well as within Mexico and Canada. With our robust capabilities and our vast supplier network, we can make just about any part you need if it's out of metal. Excellent quality for us is a requirement for our customers. We expect quality in everything we buy, and our customers are no different. Our parts wind up in everything, from fire trucks and golf carts, all the way to massive agriculture and earth-moving equipment. No matter where it goes, the parts must perform the required function in each individual application. Every step in the manufacturing process matters. Quality for us starts at the mill, as the plate, tube, sheet, or bar is created from the raw material. The mill checks the chemical composition and the strength and ductility of the metal. This certifies to Ryerson that the material conforms to the specifications by providing either a certificate of analysis or a certified material test report. Now that material properties have been verified, we must assure that the part is made correctly. This first requires a programmer to create the program for the machine to properly cut, form, or to machine the part you just saw in some of our other presentations of Jarrett. This is critical that the program is created, entered, and checked before it begins the production process. Once this is out on the floor, the machine operator performs additional quality checks. The operator reviews the processing instruction sheet and confirms that the correct program is loaded for the part being produced. The first piece of the new part that comes off the machine is checked to assure the part meets the drawing dimensions and tolerances required for the part to properly perform its intended function in the end product. These can also be called out in the title block, which Matt went over with you guys earlier. But how are the critical dimensions checked? What tools are used and how are they available? Most people are probably familiar with a tape measure, and you can tell usually within a 1/16 of the size. You use them in your house and for different projects. That's a good start, but many of our parts require a tighter tolerance. A tool called a caliper can measure parts within 1/1000th of an inch. This is a useful tool for standard length, width, or diameter measurement. If the part has a bevel or is formed at a specific angle, the operator can use another tool called a digital protractor, which can measure an angle up to 1/10 of a degree. But what if the part is large and has complicated shapes and curves that must be measured instead? So we in Ryerson also use the latest technology from laser scanners to assure a part matches the model from the customer. As you can see, these are 2D and 3D scanners we use to verify flat parts and accurately it looks over a lot of oversized different individual parts. We also have 3D laser scanners you can see that capture the complete surface of the part, which the computer software can then compare to the surface of the actual part to a perfect 3D model given by the customer. The software can even produce a color map, which quickly shows if a part is in or out of tolerance, which is extremely helpful when it comes to oversized parts or ones with large bends or odd weldment sizes. Once the parts are verified as acceptable, they move to shipping and packaging where the final quality check occurs. The parts are visually checked for appearance to be sure they are ready to go into production at the customer. The parts are packaged, arranged, and counted per customer requirements and delivered on time, ready for production. So that's just a very quick, high-level overview of quality, and I hope it's been informative for everybody. I'd be happy to answer any of your questions. Back to you, Steve.
Thank you, Professor Toth. Now that was a quality presentation. Did you know that Ryerson is ISO 9001 certified? Opening the floor for our last Q&A session. Go ahead and hit that button. We'll answer any questions that are lingering at the end here. If not, we'll get back to you after the presentation. Well, I hope everyone had as much fun as I did going back to school today. To recap, Matt Stelzer educated us on Intro to Fabrication, the elements of a print, and its impact on choosing the right fabrication path. Zach Hicks walked us through the decision criteria building a lawn product supply chain. Ray Fleming laid out the different options when processing plate products. And Jarrett Jones talked sheet metal cutting and forming. Ian Toth wrapped it up with how Ryerson manages the quality process through each step of a project. How can you find us? Check us out at ryerson.com. Check out Cup of Joe, our monthly metal commodities podcast, presented by Nick Webb, who's our Director of Risk Management and Commodity Hedging. It's available on your favorite podcast platform. You can review last year's Metal 101, covering the basics of metal, or on Ryerson's YouTube channel, as well as watch this presentation. Check out Ryerson Advanced Processing's dedicated website for detailed information on our services, market intelligence, and more at ryersonadvancedprocessing.com. And don't forget, if you want any help with any prints or any processes or RFQs, please email us at rap@ryerson.com. That's RAP@ryerson.com. One question from the floor. Ian, you didn't quite escape. How fast do those laser scanners process parts, say something the size of a human hand?
I would say it really depends on what the part is and the size of it. If let's say you're scanning a weldment, for example, if you were going to use a typical tape measure and calipers for that, it could take you a very long time to get every curve, every side of that, depending on what the print's calling out and how tight your tolerances are. The laser scanner is really nice when it comes to big, oversized parts like that, or ones of a lot of different radius, because you can just do a direct comparison to the customer model.
Thanks, Ian. Well, congratulations to all the graduates of Metal 102. Now go forth with this knowledge and fabricate successful solutions for your organizations. Thank you and goodbye.